Hi folks, welcome to another Cancha tutorial. Today you're going to talk about subcell block modeling. Uh, there's two reasons why you might get a strange block model like this one that we can see now. You can see that the blocks are all separated. They're kind of dots rather than proper blocks. They're not connected. This is going to cause problems in many respects. If you go here looking for transferring the data to a plane, you'll only get these dots. Very hard to find. You can see that there's no continuous information, so transferring that information, for example, to drill holes or metallurgical samples won't work because you'll have very short intervals and won't cover the whole sample, so it won't really be valid. The idea is if you see this sort of thing, this can also be very heavy on the computer processor. So often these sort of block models are many gigabytes in size, and if you don't treat them properly, then you'll get very low performance, and everything will take a very long time to process. So in the last video I showed how this might be coming about because of the rotation of the block model. But in this case, it's probably going to be because of the subcell reason. So if I just bring up a PowerPoint, I'll explain quickly how subcell block modeling works. Geological resources don't follow sort of neat, rectangular grids. They don't. The rock and geology in general doesn't behave like Minecraft. It doesn't have all the ore and waste in neat, tidy blocks. It comes in irregular shapes. But stopes and geological models obviously can't be easily represented for the computer. So when you're trying to do scheduling or mine planning, it's much more convenient to put a regularized grid over the top. So regularized block models are fantastic because it sort of summarizes the blocks like this. And you can easily do computer software like the Loesch-Grossmans for pit designs and whatnot. But obviously there's mistakes. There's some areas that are including waste where it should be ore, and there's other areas where it's saying that it's ore where it should be waste. So people who much smarter than me decided that we should do subcell blocking. So they divide the bigger blocks into smaller blocks in some of the cases, not in all the cases. So this is just where it provides extra detail and extra reward for the mine planners if they're able to do this. And as you can see, it much better matches the real geology. So decreases the risk for them on the resource estimate. Unfortunately for us in geometallurgy, it really doesn't matter. Like all we're using the block models for is transferring data from, whether it's ore or waste or, what ore zone it's in, which we really don't usually need this level of detail. It's very, very refined. So what we end up with, rather than a regularized block model, which Cancha prefers to deal with, you end up with all these extra blocks as points. And because the block model format itself doesn't actually come with blocks described, what it does is it describes points. And then the software, either mine planning or metallurgical software, like Cancha, has to decide how to interpret those points into a block around it. So you can see here we've got these extra points that came about the subcells, and basically what we do in Cancha, we just put regularized cells over the top. So we say, let's just keep it regularized. So this might mean that in some cases we'll have 3 points of data in one in just one regularized cell. Now obviously going back to the previous slides, you can see that in this case, this one here is ore, this is waste, and this is waste. So we've got sort of 3 cells that are in the bigger block. 1 is ore and 2 are waste. But basically what we do in Cancha, we just say last in stays. So just going down the CSV file as it's importing line by line, whichever the last of the 3 is that's imported, that's the one that's going to stay in Cancha. It's going to be visualized. That's obviously creating error and we understand that. We're not using Cancha for resource estimation. We're not using it for calculating reserves. All we're doing is it's a useful tool in order to project in an easy way information onto geometallurgical samples. If when you're reviewing the data, if you decide in your project that there is issues, then I suggest that you work with the mine planners to have a regularized block model with a smaller regular cell size. Otherwise, if you're just like me on all the hundreds of projects I've been involved with, this is really quite fine. Just use a regularized grid over the top. It means that performance is going to be much faster. You'll be able to visualize and work with the data in a reasonable way, and you'll be able to get on with your geometallurgical workflow. If you're in a narrow vein, low sulfidation gold or silver deposit, then you should pay special attention, special care. Don't regularize everything into a 10 by 10 by 10 block, or you're going to lose too much detail. So that's the theory behind it. Now let's just have a look again. So we started off with this block model like this, with all these fine points with all their little tiny little blocks with not a lot of information between them. So what we'll do now is we'll just import that same file again, and this time what we're going to do is, here's the file, and when we import it, it's imported fine. But if we hit the advanced block model, it's just pre-visualizing, it hasn't imported yet. When we open it up, we can see here the problem. We can see that it's got a 2.5 by 2.5 by 1 meter block, which is the right size for the subcelled one, you can see. But look at all the gaps between. This is why it's causing all the problems, right? So what we need to do is find a bigger block size that'll work for these and be logical. Now it seems to me that there's about 3 and then there's a gap of 1, so it's about a 4 block chunk. So 4 times 2.5 is 10. So I'm just going to change that to a 10. Enter. And so now we can, which direction was that? That's the rotation angle. Sorry, not rotating it. We're custom cell sizing it. Apologies. So let's go 10. That's better. See, learn how to use the software myself. So, okay, you can see now that the blocks are continuous in this direction, and there's obviously 2 or 3 blocks in each bigger cell, but that's fine. At least we've got continuity. Now, in the other direction, looks very similar, so we'll do the same in the north-south axis. Do 10 again, and that seems to make sense. We've got continuity. And it just seems to make sense in that direction. Now, if we look in the Z direction, could be about the same, right? So let's go 10 there as well. 10 by 10 by 10. Starting to sound a little bit more practical. So clearly we've got a structure coming through here. So this is an interesting interface that they've done a lot of extra geological modeling on, and we're going to be simplifying all that. But as you can see, by the end of the day, we'll have a 10 by 10 by 10 grid instead of the 2.5 by 2.5 by 1. Okay, so you can see it's in here in the cell size and the advanced block model. I won't change anything else and hit next. And so now it's going to be a lot faster. If you've got a 6 gigabyte subcell block model, it can easily take half an hour to import into Cancha if you haven't done any trimming and haven't done any rotations or regularization. But now you can see it opens in a few seconds, and we can see a pretty useful looking grid here. So, if I was to bring up, like for example, the iron grade, which is anything got in here, and if we wanted to look at our metallurgical samples in this context, then you can see that there's more than enough detail for geometallurgical sample identification. And now if we do things like this with like the splitters, for example, and we move the splitters along, we can actually see what's going on inside. So, a section would be, a useful a useful diagram because we can actually see a proper cross section now, whereas previously it was just a whole bunch of tiny little dots that you wouldn't see anything. And again, if we if we were to select samples on this or put drilling, then we would be able to see the block model information projected onto the drilling and onto the met samples. That's how we do it. Just going here to the data and just forcing a block size of 10 by 10 by 10. If we want to see afterwards how we did that, we can see here in the data area, clicking on the block model, we can see information about the block sizes, the number of blocks in each direction, total number of blocks. And with subcelling, it could have easily been in the, well, let's just have a little look, the same model so here we've got 48 million blocks. Okay, so we've gone from, no, that's not even true. Is it 480? Okay, so we've got 480 million blocks on a 1 by 1 by 1. Okay, 48 million blocks. And now, if we come back to the regularized one, we can see that we're down to 500,000. So obviously a massive decrease in detail, but that's going to improve the velocity that you can work in Cancha. It's going to improve the performance, and it's also going to make the data continuous, so you can actually transfer the data from one to the next. You might be wondering why we don't just go ahead and have a subcell import feature. Well, there's about 5 different formats that different mining software uses to create this subcelling. So it's not, it's not sort of cost benefit. There's a lot more useful things that we could do with the time to develop in Cancha. We're coming up with a lot more useful features for geometallurgy. And to be honest, I think that this way of tackling it using this regularization approach gives us more than enough detail for the geometallurgy and sample evaluation and geometallurgical information. Definitely shouldn't be used for resource or reserve estimates, but that's not what Cancha is for. So there you go, subcell models.